Well, sometimes I'm thinking about delta sigma modulation or sigma delta modulation. Originally, it's named as this. Uh, delta operated in input and reference, and again, and then after that, accumulation operated. So to get sigma of the difference. So sigma delta modulation. For first order, for simplicity, what is sigma delta modulation? And there's some YouTube movies explaining going like this. There's a coffee shop, but with no change available, selling a cup of coffee, 750 yens, and you have to have several thousand bill of paper only. So you can't pay for 750 and get a change, or you lose 250 yen for a cup of coffee. So you find out the solution to make a contract with this kind of rule. Contract with the shop. If you deposit more than or equal 500 yen, you pay nothing. You gotta pay nothing. And if you deposit for the shop in less than 500 yens, you gotta pay 1,000 yen, and then 1 cup, 2, 3, 4, and blah 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 blah. At some moment, you can cancel out the deposit money going to zero. You thought. So in this case, about especially 750 yen a cup of coffee. Cost every time is 750, blah blah blah. When at first you deposit to zero for shop, so you gotta pay 1,000 yen, and cost minus pay equals minus 250, and you get a deposit for shop 250. Your deposit now 250. This means you gotta pay 1,000, and then again the difference is 250 minus 250, and the deposit accumulated is 500, and now the deposit going to more than or equal 500, you pay nothing again next time for the third cup of coffees. Then the difference is 750, so your deposit is going to minus 250. Then again, the deposit is less than 500, you gotta pay 1,000. Then the difference is minus 250. And finally, after drinking 4 cups of coffees, your deposit is cancelled out to zero. And if you stop buying coffee, it's okay. You owe nothing, or your loss is nothing. So in this case, delta sigma delta modulation means if VR is 1,000, VR input is 550, and this is the value estimated about sigma delta conversion. And the sigma delta conversion described in this diagram, being from left side and other added up feedback minus VR of which is V out after DA conversion. V out equals 1 or 0 bit when this accumulated value of Vx is larger than or equal Vref, or if it is 0 when Vx is less than VREF. This time VREF equal 0.5, which is VR divided by 2. And VR equal 1 represent exactly the same value for the AD conversion analog value, and subtracted from VI makes error. And then the error, one step delayed, makes Vx and go back to be added to the same error. One step before to the now present error and accumulating and makes VO. And so in this case, VR equals 1 and VREF equals 0.5, which means VR equals 1000 and VREF equals 500, which is this deposit criteria threshold, 500 yen. And estimated value is 75% of the 1000 VR, which means density of this one V out is much to the south. When you pay 1,000 yen, it counted the VO output is 1 and 1101, like so and so on. So the density of the bit 1 is 75% here, and 0.75 times the full range of 1,000 makes 750 yens. So you can estimate exactly the same value of the input, a cup of coffee, the cost of a cup of coffee. In this case. So this is signal delta modulation. That video explained like this, and but I couldn't start designing a signal delta modulator using CMOS circuits from this this kind of explanation investigation. I don't know why there's a limit cycle like this cycle 4 for any other arbitrary number of V, and there's no assurance existing such kind of cycle, in this case 4. So I need to examine more, and in this case, the specific several cases, just about thinking about the contract with the shop, like this kind, no change available, and some 100 yen, and you have only 1,000 paper bill only, 10,000 or something, and you need to make contract deal like this kind of deposit, or if you owe 500 yen, you gotta pay 1,000. More than 500 you owe, you instead pay 1,000, or you owe the shop or less than 500, you don't need to pay. And this change the rule for this makes the same discussion like this. At the moment, at first you owe nothing, so you don't need to pay, but you owe 750. Then again, you need to pay 1,000, and difference is minus 250, and accumulated 500. But then 500 is more than this, and you need 2,000 to pay, and minus 250 difference makes your deposit. You owe 250, so less than 500, you don't need to pay, and at this moment, blah blah blah, like this going. Then you find out this is 1,250 minus 250, 100,000 minus 250, 750. Now 1,000 minus 250 and 500. This is the same. So picking up this 4 sample, cycle 4, shifted one by one, step by step, every step. After that, picking up 4 quantity series makes the error every time. Summation with the error adds up to 0 every time, every sample, and so it's actually it has a cycle 4 after you drinking 2, 3, 4, 5, 6 drinking. After 6 drinking, but in this case, you owed 500 to the shop, so they must be paid 500, but you don't have 1,000, so you need more drink, and then that's you owe 250 or you owe 1,000. At this moment, you can pay 1,000 and stop buying it, and it cancels out the balance completed. So, or this is 1,000. You can stop. You can stop if you stop there. It seems okay, but actually there's no cycle matched. So this at this point you can stop. You can stop, and you only pay back to 1,000 yen after drinking 8 cups of coffee, and so 1, 2, 3, 4, 5, 6,000, 8 cups of coffee or 750 is balanced. So instead of applying this rule, if you apply the owing rule, you need to pay back extra money you owe to the shop, and appropriate cup of coffee needed to finish. And then on the other hand, this is 750. And this case is making rule contract with the shop by deposit base, and but price is 250, and then at first you don't deposit 0, and then you pay 1,000, and 250 minus 1,000 minus 750. So you deposit 750 to the shop, and you have more than 500 deposit, you pay nothing, and 250 deposit 500, still pay nothing. The deposit is going to be 250, so you need to pay next, and then going blah 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 blah. And actually, after 8 cups of coffee, you will deposit 1,000 when the price is 250, but it's has a sequence, and this sequence, or this is 1,000, this is 1,750, 1,000, this is sequence. This can be okay, and this one is 0 to 50, 0, 500, 0 to 50, 500. This is cycle 4, and this you can stop this, but you only have 1,000, and you need or no. In this case, deposit rule. So you can pay back after drink 8 cups of coffee, 1,000 yen. No change available, but only 1,000 yen bill they have. So you, after drinking 8 cups, you paid back the 1,000 yen. But at this moment before, you can't pay back because they have no change, also exchange. So this is your payback cases. Also, you need to extra drinking a cups of coffee. Need enough cups of coffee, and then you can stop buying it. And on the other hand, when you apply the rule of the owing rule, I wrote it there. VR equal 250 yen, and as first you owe nothing, so you don't pay. But the 250 minus 0 equals 250, so you owed 250, but you owed just less than 500, so no, you got pay nothing, and you get 2 cups of coffee, and after that you owe 500. So it's this in this case you need to pay. You gotta pay 1,000 next time, and minus 750 makes deposit you owe of minus 250, so you don't need to pay, and it's going to 0. You owe nothing again after 4 cycles. So cycle is 4 exists, and in this case, if you have if a shop is buying a cup of coffee or each cup of coffee 250 yens, and they have no change available, and the paper bill you only have several thousand paper bill, and in that case you can stop after 4 couple or multiple of 4 couple. Every time balanced, and summation of the error is going to 0 each time. So you need to select rules, deposit rule, all rule appropriately. If you select appropriate, make appropriate contract rule, you can stop cyclic without any payback and compensation when you stop it. But you need minimum cycle n. Or more than n. Now you need to appropriate a cycle to stop and pay back or pay compensate. This moment yours for 750 owing rule applied 0. You owe nothing paid, but you owe 750. You need to pay 1,000. Still 500,000. 250 you don't need to, and 1,000 you owe 1,000, so you need to pay. 750 you need to pay. 500 you need to pay. 200 you don't need to pay. And then like this, you need to pay at this moment 1,000 yen because no change available. So you need to. And also you have only parts of paper bill 1,000. So when you stop buying to balance, you need to drink 8 cup of coffees. After that, you gotta pay 1,000. This is all to the shop, and I already explained 6,000 yen for 8 cups of coffee. And so you need to select the rule, well, whichever you like. But this is very efficient for 750, and this is very efficient for owing rule is very efficient for 250 yen cup of coffee. By the way, this talk is about what? C model modulation, but I couldn't apply the design method understanding of these specific cases and making rules. But BR over half, like this 500, is very symmetrical. Half point, no deposit overshoot, accumulation overflow is appropriate. So in general cases, there's appropriate threshold judging point, but owing rule or depositing rule is actually makes different. So we need to choose appropriate one for the target input. But we couldn't change the rules of the circuit comparator reference voltage because we don't know how much value input comes. So we need to decide each one. So this is signal delta modulation principle, but I need to examine in which the cycle of M exists or not for every arbitrary V in, Vi, this Y. So then I'd like to show my thinking in case A and in case B. I wrote the diagram, two kind of diagram, and this leftmost one is the general cases of root filter H of Z and feedback filter H of Z, F of Z, HZ and FZ. And in general, V out is H over 1 plus FH, Vi plus 1 over 1 plus FH, VQ. VQ is a quantization noise added to the output comparator. And so we need to accumulate value to the 1 or 0 bit value judged by the reference voltage. In this case, Vx more than equal Vref, V out equal 1, bit 1, and the other case is otherwise it's 0, 1, 0 is D converted to VR, and it's VR equal 1 because it's convenient, and Vref equals half, Vref equals half VR. To judge here, as I mentioned in the explanation before, with specific couple of coffee shop cases, and what are they? And this has delay, one step delay, 0 to -1 in the feedback loop. This is nothing. And key point is a delayed integrator or non-delayed delaying integrator. Delayed integrator is d to the -1 divided by 1 minus d to the -1. You can derive this transfer function in Z space, frequency of the Z space. Z space means just a phase shift of sinusoidal signals, like exponential minus j omega t sub s. T sub s is 1 over f sub s sample frequency, the sampling period. And so, it's just omega 2 pi frequency f divided by f sub s. And this is 0 to -1, and simplified notation made, thinking the system model easier, and just phase shift, time shift of TS delayed, one step flip-flop delay, clock count. So if this is d to the -1, 2 TS delayed. right, and so on. So it's not so difficult mathematically. What does these things mean is somehow difficult. So in case B, there's a latch for some kind of metastability. This comparator might not be sharp enough output. Having this output might not be sharp enough. In that case, some instability happens. So avoiding metastability by first latch, we apply fz of z minus 0 to minus 1 before DAC. And simplified like this. And in this case, the comparator having a latch and very fast comparator, and it might have very sharp enough edges, one and zeros. So this is simpler. So I'd like to explain with this case A. In general, this is these H and F is for A. You can, for this is the minus 1, this is the minus 1. For this, 1 minus 0 is the minus 1. And for B, this is just 1. And for this B, this is 1 minus 0 is the same. And you can derive from these converted diagrams very easily from here to there. And this from this insight, we can see when z to the minus 1 frequency going to f equal approaches 0, this is 1. So 1 minus 1 going to 0. So added quantized noise affects nothing. This part going to zero up when f approaches 0 DC level. So for constant Vi, we don't care for this B, Q. And this is 1. So output is just exact value of Vi. When Vi equals DC, especially. Now this is noise shaping. These are noise shaping effects. It's almost the same. Or it's the same. And just this is one step delay, no delay, and having a latch. So sometimes it's very effective and reliable, more reliable. But usually we can use this sharp comparator applying sharp comparator, fast comparator. Like I said, I select case A and explain why we have cycle N in specific input numbers, X, Y, which is described as a rational number of binary series, which is less than 1. So when Vi is written like this, which is we are going to summation of 2 to the case and A sub j, j equal 1 to m. No, last case j, j. So this is 2 half plus 2 plus 2 to the case 1 over 2 to the case, and this is A1, A2, and AK. And K is J, AJ equal 1. Maximum K is maximum J where A sub J equals 1. Maximum J. The rational number can be represented like this. But real number have irrational number, and we don't explain. I don't explain where the exact cycle exists. Maybe we need to interpolate the rational number points. Interpolate because this rational number has this kind of expression and has an exact cycle of m, and if we select the sample m and makes the words of it m-bit words and applying appropriate filtering, moving average, etc., we can express, we can recover the input after filtering. A AD convert and DA convert, recovering DA, recovering after applying interpolating filter, like CIC, cascaded integrated cone. For example, if you know whatsoever. So rational number case is very effective, I think. And then if we are in this case, we have some cycle m, must be. For accumulator, watching for this accumulator loop, we got Vx of n equals Vi sub n minus 1 minus Vr sub n minus 1 plus Vx before one step before Vx sub n minus 1. And then from this series equation, Vx sub n equal Vr n minus 1 minus Vr n minus 1 exchange error of n minus 1 plus Vx. This is expanded to n minus 2 and plus n minus 3 blah 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 plus n minus something plus finally Vs of sub n minus m. This is and then for m cycle, m is when m is a cycle of this system, Vx sub n equals Vx sub n minus m before m step. So then this is m plus 1, m minus 1, m minus 1 minus m minus 1, so minus m plus 1. So this is summation with respect to j equal n minus m plus 1 to n minus 1 of ej. In this case, this is going to 0 because this cancelled out. So m cycle picked up m cycle error added up to 0. This is, which means exactly the same value after having m cycle. So you can capturing m sample and filtering out to get the interpolated value of the Vi very precisely. So, but how much m needed? please think about this. Like if this multiplied by 2 to the k, this part going to all of the terms multiplied by 2 to the k's. This minimum value is actually a sub k equals 1 because k is the maximum of j while a sub j equals 1. So this makes this going to be 1, the minimum integer. So this makes some kind of count of a1, a2, blah, 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 ak, whatsoever, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, something. One bit count of one bit 1 is this value. And then this is minimum counts applied. If we multiply 2 to the k plus 1, it's once again doubled, but no need to doubling this. I mean, for getting cycle, so actually this is the cycle M. So there exists a cycle of 2 to the k's. So if VR is expanded like this by binary sequences below the decimal points at an app, then the cycle M equal to the k. K is the maximum j, index j of a sub, where a sub j equals 1, coefficient equals 1. So we got, in case we know this expression, each this y. But there are many this y of this kind of rational number in actual continuous VI. We can interpolate these values. These values are always having, with sampling m, no errors on average. So exact VI is in each rational number is explained with 3 to 1 and 0 as a density. Density D equals m cycle of volume into C counts of mass, C over M. So count and density like that 75% multiplied by VR, dVR, full range. This is full range of the converter, signal delta modulator, full range. Density full range makes count, which is VI, or VR average value, actual constant, where VR constant, each constants. So VR is 1 and density is 0.75, the input is exactly 0.75. 75% of 1 is existing cycle M. So this density makes good approximation for VI. Very good. And now we need to interpolate using some kind of CIC filter or whatsoever, you know. Then actually there are some cycles in each rational number. This is 1,000 times multiplied by the density to explain the price of the cup of coffee and your paper bill. 1,000 yen, but it's the same. You can expand the rational number sequence of 1 over 2 to the kth, 2 to the jth, and approach limited cycle, limited digit number of integer, series integer, or below the decimal points. In a given decimal numbers, limited accuracy, we can precisely interpolate the input value by catching up the expected cycle m. Each word having enough minimum value of cycle n bit words. So this is sigma delta modulation principle. It actually explains the special specific cases that we need to interpolate the rational number between rational number. Rational numbers, in a sense, limited series given for a given accuracy is explained exactly correctly by utilizing this sigma delta modulation after utilizing some appropriate filtering. See, I see like whatever, you know. And the output bit sequence density is the B in every time. This is first order. And the other issues of stability are which I deleted already. Sometimes you need to change this delay type accumulator or integrator into the non-delayed integrator and apply one step d-1 delay to the feedback for metastability, avoiding metastability. But in many cases, I see there's no metastability for fast latching clocked comparator. But for RF application, maybe the textbook of RF application describes the type B diagrams. So they need some kind of diagram like that and topology of the circuit having latch into the feedback for metastability, for avoiding metastability. Oh, it's 43 minutes explanation. Are you okay?